Here we're going to look at the concept of strain energy and how we can use that to solve solid mechanics problems. And we'll start with Hooke's law, the classic law that we all learned and took as our first lab experiment in physics. And I'm sure that you'll remember that F is equal to Kx, and we tend not to worry about the negative so much. We understand that it's opposite of x. And you might recall your very first lab, we made a plot of x versus force in the spring, and we loaded it up with different weights, and we generated a plot to prove the linear nature of Hooke's law, and the slope k was our spring constant. And it came out with units of newtons per meter or pounds per inch. And it turns out in solid mechanics, everything is a spring. And what I mean by that is the linear nature of deformation. And in fact, most things respond linearly. It's rare and actually quite difficult to try to make a non-linear spring. Let's see how we can use that concept to solve problems. Well, recall for springs, the spring energy is really just work done by a spring or stored in the spring, and it's equal to the integral of F dx, our general form for work, which would be the integral of Kx dx, and that would usually go from 0 to x, and we would get 1/2 Kx squared. Now you might recall that we can also calculate the work done by a variable force as F average times distance, where the average force in this case, if we're going from 0 to x max, we'll find that F max will be Kx max. And the average then would be from 0 to F max. So that would be 1/2 of F max times the distance, which would be x max. And looking over here, we see that F max is Kx max. And we'll get 1/2 Kx max squared, our spring energy equation. And this is the area of a triangle, 1/2 base times height. And that tells us that the work done by a variable force is the area underneath the curve. And we can use the average force over the distance, if it's a linear relationship, to compute that. So just a graphical way of computing the energy. But there's some other very interesting things we can do with this equation. For example, who says we have to write it like this? If we look at Hooke's law, x is F over k. Let's put that in here. So the energy in a spring will be 1/2 k F squared over k squared. One of the k's drops out, and we get 1/2 F squared over k, which is an alternate form of the spring energy equation. So it turns out we could write the energy equation in terms of the load F or in terms of the deformation x. In solid mechanics, we often know the load or the weight that's been applied to something, so why not use this form rather than finding out the amount of stretch that something's had and going through those extra steps? So you'll see that we tend to use this form more often. Here we have a very simple rod of length L and modulus of elasticity and cross-section A, and we apply a force on there, and we'll see that it'll deflect down by some amount of deflection. And we have an equation for solving that. Deflection is FL on EA, our so-called Flea equation. The goal here is to reformat this equation so that it looks like Hooke's law and to reveal the linear nature of this deformation. So here we have F, and this is in effect our x value. So let's rearrange this. So F will be EA on L times the deflection. And what we have here is the K effective for that rod. And note that this is a linear relationship. As the load increases, the deflection will increase linearly as well. So it is a Hookean material. Now if we plug that K effective into our spring energy equation, we can say then that the energy stored in that rod would be 1/2 K, which is EA over L, times the deflection of the rod squared. Or if we want to use this alternate form here, it'd be 1/2 times 1 over K, which would be L over EA, times F squared. And again, that's a fairly useful way of doing it. We usually know the force more so than knowing the elongation, although either one of these will work. So this becomes our go-to equation. So the energy in a rod will be 1/2 F squared L on EA, our so-called superfleet equation. Ooh, super flat. Super flat. Here we have a 1-pound hammer that we're going to model the strike as if it were dropped from 2 feet, and it hits a 16-penny nail that's sticking into some wood, and the nail is 2 inches above the level of the wood, and we strike it, but the nail doesn't move. Find the force P developed during the impact. Well, we can start with the energy of the blow, and the energy in the hammer will be potential energy as mgh, which eventually turns into kinetic energy and then turns into energy inside of the nail. So we'll just go with that for now. And mg is the weight here. We have to be careful with the English units because that's weight, not mass. So this will be weight times height. So we get 1 pound times 2 feet. So the energy in the blow will be 2 pound-feet of energy. When it strikes the nail is going to compress. So we can say then that the energy stored in the nail will be 1/2 P squared L on EA. Ooh, super flat. And the energy stored in the nail will equal the potential energy that the hammer has brought to the impact. So we'll end up with 1/2 P squared L on EA will equal 24 inch-pounds. So P will be, the E of steel is 29 times 10 to the 6. The length of the nail is 2 inches, and the cross-sectional area we can calculate quickly. Area is pi d squared on 4. So that'll be pi times 3/16 squared on 4, 0.0276. And from that we'll find the force is 4384 pounds. We could ask how much stress did that generate. So the stress in the nail would be P over A, which would be 4384 divided by 0.0276. And we'll find that we have a stress, we'll get 159 KSI, and 36 KSI is the yield point. So we would have deformed this nail some and compressed it and striking it that hard. Now we also could ask, could it possibly buckle and bend the nail? Well, let's check that. P critical for buckling would be pi squared EI on length squared, and that would give us pi squared 29 times 10 to the 6. I would be 1/4 pi, and r to the 4th, which would be 3/32 to the 4th, over length effective. Now length effective is interesting here. This nail is stuck firmly in this block of wood, so that makes it fixed free. And recall that length effective is 2 times length actual for fixed free. This nail is going to bend like that, and we'd have to go twice that far to recreate that half of a sine curve. So down here we'll end up with 4 inches squared, and that will give us a buckling force of 1085 pounds. So if we hit this directly on, we're probably not buckling it. We are yielding it and compressing it. It will be slightly shorter after the impact. Here we have a cantilevered beam. Think of it like a diving board. And we're going to drop a weight onto it, and the cantilever will deflect downward when the weight lands on it. And recall that we have a set of tables to define this type of deflection. Now, to use our energy methods on this, we have y is equal to PL cubed on 3EI, and we have to rearrange that as F is equal to KX. We need to figure out what the K effective is of this cantilevered beam. So we have y is PL cubed on 3EI, and P is the load, F, and y is our effective x in Hooke's law. So we have P is 3EI divided by L cubed times y, and that's our K effective. And note again that it's a linear relationship. Everything in here is a bunch of constants, and our two variables are out here without powers, so that is linear. So this is a Hookean effect. And from here we can then use conservation of energy, and the potential energy of the block will be mg h plus y max. And the reason we need to write it this way is we like to call the lowest point in the system h equal to 0, because as the block falls, it's still giving up gravitational potential energy while it's deflecting that cantilever. So we tend to measure height from the lowest point. Once the mass reaches this point, all the energy is stored in the cantilever and it's ready to shoot the thing back up in the air, most likely. So we have two forms of the energy that we can use. We can do energy as 1/2 kx squared, or we can do it as 1/2 f squared over k. And in this case, we're going to use the form 1/2 kx squared because we want the deflection. We're not asked for the maximum force, although we could find it. So this will equal 1/2 k, which is all of this, 3EI over L cubed times y max squared. And if we rearrange this, we'll get 3EI over 2L cubed y max squared minus mg y max minus mgh is equal to 0, which we can solve using the quadratic equation. And if we plug in our values, we could find two values for y. One of them we'll omit, and we'll find then that y max will be greater than the y static. Let's say we have a rigid disk attached to a rod of length L, and we know all the information about this rod, and we're going to torque this, and we anticipate the disk to rotate by some angle of phi, in which case this rod acts like a torsional spring. As we torque it, it's going to try to return the disk to its original spot and probably even push it past it, in which case we'll get harmonic motion as the disk oscillates at the end of this spring. Recall from our torsion discussions that phi is TL on JG, and compare that to our Flee equation where we calculated elongation based on F. Now we can use torque. We still use L. Instead of the E modulus, we use G, shear modulus. And instead of A, we use J, the polar moment of inertia. So this is an equation that we used to calculate the angle of twist in radians for a given rod. And again, let's rearrange it so it looks like F is equal to Kx. So the torque is our equivalent of the force, and the deflection is our equivalent of x. So we'll get then that T is jg on L times phi, and again note that that's linear. So there's our K effective, at which point we would now have the energy stored inside the rod will be 1/2 K jg on L times phi squared, or 1/2 L over jg times torque squared. But notice how any of our equations, if they're linear in nature, we can extract the K effective and use it right away inside of our energy equation. Undoubtedly, one of the most powerful uses for strain energy is determining the deflection inside of a truss or a complicated system. Here we have 5 different members and one load being applied, and we'd like to find out how much deflection does that load cause. Now, one way to do it would be to go through and calculate the force calculate the force in each and every one of these members, and then apply our Flea equation and figure out how much longer each member is, and then reconstruct this thing using the new geometry that we've got to figure out how much it's moved from its original position. And that's an incredible amount of work. However, we can treat this truss as one large spring, and therefore the total energy stored inside of it, the sum of the energy in all of the different pieces and parts, will equal the work done by the force P. The energy will be the sum of the 1/2 F squared L on EA. Also then recall work done would be force average times distance moved. If you have a varying force, think of springs, and the force is increasing linearly, which it would in this case, the average force will be 1/2 P times the deflection. So we don't use the full force because the full force doesn't act over this whole entire deflection. So we end up with 1/2 P times deflection, and you can cancel out the 1/2s if you like, and we get an extremely useful equation that the sum of the energy is F squared L on EA, and that's P times the deflection. Now there's some golden rules to watch out for with this. Strain energy is not linear. We're squaring the force and we're squaring the deflections when we put it into this form, and as such the superposition principle does not apply, which means we can only do this for one load at one point on this truss. We couldn't combine loads and have a second load up here at B and then go through and try to solve this. It won't work. We could solve the deflection due to a load at D as one calculation. We could then solve a separate calculation for the deflection at B, but we could not add those deflections together. That's not allowed because superposition only applies if you have linear relationships. And the second rule to follow is that you can only measure deflections in the direction of the load, and that's due to the way that work is calculated. Work is force times distance in the same direction, which is often the case. We apply it with a uniform load. However, if the load was off at some angle, we couldn't break this apart into components and work on that because, again, superposition doesn't work here. We can't treat it as two loads. Here we have a truss made of wood. We're given the geometric values of the E of the wood is 2 MSI. The cross-sectional areas are given as A and 2A, where A is 2 square inches. And we're asked to find the load P, which will cause a 1/2 inch deflection at NC. So out here at C, we're going to move this down by 1/2 inch due to this load. And that's going to put all these different members in compression and tension in order to do that. This is the perfect type of problem to use our strain energy equation, where our strain energy equation is the sum of the F squared L on EA is P times deflection. Although we don't have the 1/2s in here, we've canceled them out. Since we have so many members, the best way to do this is with a table. Recall from statics, usually we look for zero force members first, and I see at least one, where this would be a zero force member because that pin can't have a load on it. So DB is a zero force member, and we won't need these entries then here. Let's go through and fill in the lengths first. So that's 30 inches. BC is 30. CD is 30 square root of 2. DE is 30. And DA is 30 square root of 2. We also know the area, as we're told that little a is 2 square inches. So this will be 2 square inches. That one's 2. CD is 4. DE is 4. And DA is 2. And what we're doing here is all the steps required to get F squared L on EA together. And this way we can go right across each line. So now we have to find the forces. And you can recall from statics we can do this by pins. So if I start with pin C, we have a force P acting down on it, and we'll just leave it as an unknown. And we have 2 members coming off of here. And we know that this one has a 1-to-1 ratio on it. It's 45 degrees. So summing the forces in the Y, if we have P down, we have to have P up here. This has no Y component. And in the X direction, that has to have a value of P in that direction because that is in compression. And then summing the forces in the X, we could say that this would have to be P. So that gives us member BC here, which is P. And we also get CD from that. CD will be P square root of 2. If we look here at connection B, since this one was a 0, we use Newton's third law to get to the other pin. So if this end of the member was pulling to the left, this side it'll pull to the right. And then that means this would have to be P to put that in equilibrium. So with that, we now also have AB will be P. And now we could jump down to connection D. We look at D. We have, again with Newton's third law, whatever we have here, we flip it over on the other member. So P was to the right here, it'll be to the left. And P was up, so it'll be down. And you'll see that works because that puts this end in compression, and we know this member right here is in compression. And looking at it in the vertical direction, this would have to have a P acting up in order to give us equilibrium. And as such, it would have a P to the left. And we have 2P to the left, which means this member will be 2P to the right. So that's DE. So DE is 2P. And DA we now also have. DA is P square root of 2. And we haven't used connection A yet. So we'll use A now as a way to double check our work. So if I draw connection A here, we have a P in this direction. And we have equal but opposites. We have a P and a P in this direction. But recall that's a wall mount. So we have the ability for there to be an AX and an AY at that connection. And those we'll find by doing sum of the moments about A for the entire truss. We end up with P times 60 will have to equal EX times 30. So EX will be 2P. So we know that we have 2P pushing out here on the wall, which is a good thing because we found 2P on that member as well, so that's a good check. And then summing the forces in the X direction, we have AX has to be equal and opposite to EX, so that'll be 2P in this direction. So AX is 2P here. And then summing the forces vertically, we find that P, the only downward acting force, has to equal AY. So AY is P. And now we can check this member. We have P acting down, we have P acting up, that checks. we have 2p to the left, and we have p plus p, we have 2p to the right, so everything checks out. So with that, we've got all of our forces, the lengths, and the areas, and we're ready to calculate our F squared L on EA. And the reason I don't have E in here is that it's the same. So I'm going to lift E out in front rather than drag it through every calculation, since it's a constant in this case. If this was made of a mix of wood and steel and cables, then we would have to leave E in, as it would be a variable for each of the terms. Now we can go through and calculate these entries. So we'll have 30 divided by 2. Each one of these will be divided by all the way down the line. So we'll have 15p squared for that. This will be 15p squared. Let's see, CD will be p squared times 2 when we square that, times 30 square root of 2, all over 4. P squared 15 square root of 2 for that. And DE will be 4p squared 30 on 4, so the 4's drop out, and this becomes 30p squared. And then DA will be p squared times 2, 30 square root of 2 on 2, so that'll be 30p squared square root of 2 for that one. Now you may have noticed I've gotten a little bit lazy with my signage here. AB is in tension, so that's a plus. BC is in tension, so that's a plus. CD we found to be in compression, and that's a negative. DE is in compression, that's a negative. And DA was in tension, so that's a plus. However, it won't matter because we're squaring, I have a rainbow, because we're squaring F squared. Energy is positive, whether it's compressive or whether it's tensile, we have stored energy. So it turns out it won't matter when we add these up. And our number when we put this together will be 123.6 p squared. So our formula says that P times the deflection will be the sum of F squared L on EA. If we want to solve this for P, it will equal 1 over the deflection times the sum of F squared L on EA. Let me bring E outside with that. So we get 1 over 1/2 of an inch. E was 2 times 10 to the 6. And our entire summation, we know it's 123.6 p squared. We can divide through by a p, and that'll leave us a 1 over here. So we end up with, finally, that p will equal 8088 pounds, or 8.1 kips will cause that 1/2 inch deflection. So I think you can see that this is a powerful method for solving deflections in complex devices like trusses. Now at this point we should check that these members are safe. Wood has an ultimate compressive stress around 7 ksi, and it has an ultimate tensile stress of 15 ksi. So we could go through here and check this. P we found to be 8, and we could make a column here of stress in each member. So 8 divided by 2 is going to be 4, and this will be in KSIs. 8 divided by 2 is going to be 4 KSI. P square root of 2 on 4 will be 2.82. 2p on 4 will be p on 2, which will be 4, and p square root of 2 on 2 will be 5.7 KSIs. And here it does matter which ones are in tension and compression. So let's check the ones that are in tension first. We can handle up to 15 KSI, and we have 4, 4, and 5.7, so those are all fine. They have fairly high safety factors. For compression, we can handle up to 7. We have 2 that are in compression, so 2.82 and 4, so we're going to be okay in terms of tension and compression. And then lastly, we really should check it for buckling too, where P critical will be pi squared EI on length effective squared. And in this case, they're all pin to pin, so the effective length is the length. And we're only concerned about members that are in compression and that are long. So if we take a look at that, we have 2 that are in compression, ED and DC, and those just happen to be the members that are double the size, and all the members in here are made from 1" by 2" wood, and those specific members were doubled up to be 2 by 2. So the I then, and we want I minimum here, it's 2" by 2", it's a square. So I will be 1/12 BH cubed, which will be 1/12 times 2 to the 4th, which will be 16/12 or 4/3 inches to the 4th. And with that, we could calculate P critical. We'll do it for ED first. So P critical for ED will be pi squared 2 times 10 to the 6 for E, 4/3 for I, and the length effective is 30 inches squared. And I get 29.2 kips, which is a fairly large load. We don't have anything near that, so that member is okay. And then we can check P critical for DC over 30 squared square root of 2 squared. Everything else is the same, and square root of 2 squared is 2, so this will be half of that. So that'll be 14.6 kips. And again, we're well below that, so we're okay in terms of buckling. Now, curiously, if they hadn't doubled those up, would it have been okay? Did the designer know what they were doing? Well, the I would be, and we have to do it for the minimum, so that's 1 by 2 now, so the I would be 1/12 2 times 1 cubed, which would be 1/6. So we put a 1/6 in here and a 1/6 in here to check these. So if we had made it from the 1 by 2, this would buckle at 3.7 KSI, and this would buckle at half of that, 1.83 KSI. And if we look, they're both well above that, so we would have a buckling problem if they hadn't doubled up those 2 specific connections. In this case, though, our truss is okay. It will withstand the compressive tensile stresses, and it will withstand the buckling loads that are being applied to it. So the strain energy methods are extremely useful. We can use them for calculating impact events with different types of beams or structures by converting to the Hooke's law equivalent, or they're extremely handy in the case of compound structures like trusses. Thanks for watching. Ooh, super fast.